Thank you so much for inviting me to speak at the 12th China Cognitive Linguistics Conference. I really regret not being able to join you in person, but hopefully we will meet in the not too distant future. As you can tell from the title of this talk, Towards a Computational Cognitive Linguistics, in today's talk I will present some of the work I've been doing with my team on using computational models of learning in cognitive linguistics. And we are pursuing this merger because of a very specific reason. Usage-based linguistics is built on the assumption that languages are dynamic systems that emerge from and are shaped by usage in a process that's mediated by general cognitive abilities and functional considerations. The general cognitive abilities that have received most attention to date are classification, abstraction, or imagination. Cognitive constructs have received attention too, although not always as much as would have been expected. Examples here are memory and attention. Take memory, for example, which isn't widely discussed, even though frequency plays a crucial role in usage-based approaches, and frequency effects are, in essence, memory effects. So it seems that despite our interest in the emergence of structure from use, processes or functions that would enable growing a system from use have been absent from usage-based considerations. In fact, learning constitutes our very own elephant in the room. Learning was vigorously exiled from the linguistic landscape by Chomsky's criticism of Skinner's book Verbal Behavior. And although recent years have seen a resurgence in the interest of learning, it's still to make a full comeback onto the linguistic scene. The review that Chomsky wrote of Skinner's work, and that got published in the journal Linguistics, was shockingly beside the point. Skinner had been sent an earlier 60-page version, a draft version, but had stopped reading it 6 pages in. He said he couldn't identify at all with what the review was addressing. But Chomsky's review was amazingly efficient. Prominent psychologists such as Broadbent and Osgood also published reviews of Skinner's work, and they did so in reputable psychology journals, but they never achieved what Chomsky achieved with his review in a linguistics journal. As Knapp wrote in 1992, between 1972 and 1990, as you can see on the graph here, the review of Skinner's book Verbal Behavior by Chomsky was cited once for every 2 citations of verbal behavior itself. This is a very unusual relationship between a book and a review, and perhaps it's unique in the history of the social sciences. Nick Ellis, whom you see on the picture here, was the first in 2006 to reintroduce concepts and measures from learning theory to the study of language learning and the study of second language learning in particular. And he followed this through with a series of case studies that investigated typical learning effects such as blocking and overshadowing in L2. However, I got interested in learning from it for a different reason. I was looking for a way to ensure the cognitive reality of the categories and labels I was working with. So, as a cognitive corpus linguist, the real conundrum for me was, and still is, knowing whether the patterns I find in my data are real. And with real, I don't mean do they exist in the data, because sure, they do. They exist, we found them. With real, I mean, are they real for naive native speakers who aren't trained linguists? Which regularities are discovered and exploited? What do these patterns look like? Do we need to make sense of these patterns? That is, do we need to interpret and label them semantically? Those are some of the questions that bug me. And one way for me to get a handle on this is via the concept of learning. Linguists are, in a sense, interested in the end result of learning. And we like our knowledge neatly organized, as in this tool cabinet here on the right, which has a space for phonemes, morphemes, lexemes, constructions, you name it, it's there. And psychologists are interested in the process of learning, how the rat learns to navigate the maze. We think we can fruitfully combine these partial interests of psychology and linguistics because the process can help us understand the end result. We can let learning constrain the linguistic units and generalizations that theory allows, and this is a way, for me at least, to honor the cognitive commitment by which all cognitive linguists are bound. But we also think that the end result can help us reverse engineer the process. So we can let the linguistic commitments inspire new insights into intricate aspects of learning. What does a theory of learning, a system of learning, need to be able to handle to account for language, which is one of the most complex systems humans learn to handle? And also, it sheds further light on what needs to be learned to learn a language. This is the research program that we are pursuing with the Out of Our Minds team, which I lead together with Petar Milin. Our work has so far focused on what learning can tell us about language, that is, about how language works, and also on how data from language can challenge theories of learning. In today's talk, I will present some of the work we are doing on understanding aspects of the verbal system, and I will show how we factor in learning by using computational techniques that implement principles of learning. We feel that such an approach provides valuable insights into the kinds of generalizations or abstractions that can lay claim to cognitive plausibility, and this approach may ultimately alter the way in which we think about language. Now, before I proceed, I also want to put two disclaimers in. When I use computational models, I'm not aiming to do things as well as is computationally possible. As a cognitive linguist, my interest is in doing things as cognitively plausible as possible. Linguists of different convictions may have different concerns, such as economy of description, for example, and those concerns are equally valid. I am also not trying to convert the world to learning, let alone trying to convince anyone that learning will solve all the problems of linguistics. It won't. But I do feel that learning has something valuable to offer the usage-based community, who need to show how abstractions emerge from exposure to usage and what cognitively realistic abstractions would look like. So now to move to today's case study. The case study that I will be presenting focuses on the tense aspect system in English, and it's a study that was carried out together with a current postdoc on our team, Dr. Laurence Romain, and a former postdoc on our team, Dr. Adnan Azizi. The paper has now been accepted for publication in Cognitive Linguistics, and it will be available soonish, so you can read all of the details there as well. This case study is, in essence, a study on time in language. But what is time? That's a question that has kept many disciplines busy for centuries. Linguists are particularly interested in how time is expressed in language, and we rely on the concepts of tense and aspect for this. Now, I've put a table of contents, the first page of a table of contents of a monograph on the topic by a leading scholar, Robert Binnick, here on the slide. And you can see that these concepts have a very long and very problematic history. Tense is the easier concept of the two. Tense is a way of locating events in time relative to the time of speaking. It's been debated since antiquity, though, as you can see on the screenshot on the table of contents. So we have ancient theories of tense, we have traditional theories, modern theories, and we are now ready to go beyond theories of tense. But what is aspect? As you can see in the table contents on the right, aspect is a problem. That's the first thing, that's the title of the first section on the part that deals with aspect. And aspect has been said to reveal to the different ways of viewing the internal temporal constituency of a situation. If that means very little to you, don't worry. Most linguists who work on aspect don't really know what it means either. But linguists are happy to put their conceptual doubts aside, and they use these concepts, tense and aspect, for descriptive purposes. So generally, grammars of English assume the existence of 12 tense aspect combinations, and these arise from the combination of 3 tenses in red on the slide and 4 aspects in green. And those are represented in this table here. So on a grammatical approach, you would define the abstract meaning of each tense and each aspect separately. Tense is, as I said, relatively easy. If I talk about something that happened yesterday, I will use a past tense. If I talk about something that will happen tomorrow, I will use a future tense. And if I talk about the now, I use the present tense. Aspect, although more complex, can be explained in the same way. So the simple aspect is used to express a fact. The perfect aspect is for actions which are completed but retain some relevance to the present situation. The progressive aspect describes an event that takes place over a period of time, and perfect progressive is some kind of combination of both. And now you can apply those concepts to unsuspecting verbs, to any verbs really. We get the following. It's a very economical approach. You just swap the verb you're using, put it in the correct cell, create the correct or the corresponding form, and there you go. You don't even notice how terribly inadequate this solution is until you try to use it to teach the English tense aspect system to foreign learners of English. A corpus-based approach yields much more useful results. Corpus linguists may use the same categories, tense and aspect, but they stay close to the relation between verbs and tense aspect markers. For example, Bybee and his colleagues found that the verbs that are the most attracted to the present denote mental and logical states, such as I bet, you know, and I mean. Verbs that occur most in the past are verbs denoting events, especially speech acts, such as he replied, she nodded, they remarked. There are also verbs that prefer the present perfect or the present progressive. And Bybee and his colleagues also noted relevant properties of the context. For example, that the past perfect is usually found with time adverbials such as since then, so far, or recently. Now, this is probably something that many in the audience will be able to relate to. And it's also an account that's much more directly useful to learners, but at the same time it looks like madness. Within theoretical linguistics, researchers who have considered this so-called lexical option or lexical approach to tense and aspect have always tried to reduce the lexicon to a limited number of categories. Wendler had 4, his Russian predecessor had 20, but here we might have hundreds and hundreds per cell. So then the question arises, do we simply memorize each individual item, or is there some system to this madness? And to answer this question, we trained our computational model, which learns from data the way humans do, to select a specific tense aspect form given the sentence context. And we did this because, as I stated in the introduction, we think that learnability is a way for us to operationalize emergence and to guarantee cognitive plausibility. So if language knowledge emerges from exposure to usage, then any categories we assume exist in the minds of language users should, at the very least, be learnable from input. And that is exactly what we wanted to test in this study. So we will be asking 2 related research questions. Are all English tense aspect combinations equally learnable, and what information that is available in the context supports each of these tense aspect combinations? And we will use that information to determine what the coordinates are of the English tense aspect system. So which dimensions of experience does the tense aspect system encode if we don't tell it about tense and if we don't tell it about aspect? Now, before I continue into the actual training study, I have to put 2 disclaimers in place. So the first one has to do with the future. As you will know, there is a discussion about the future tense in English, and the question is whether English has a future tense. This question is triggered by the fact that the future isn't morphologically marked in the same way as the past and the present are. The future requires the auxiliary will or a going to, gonna phrase, whereas the past and the present have their inflections directly added on the verb base. So Michaelis, for example, in her 2006 book describes the future as a periphrastic construction and considers it as different from the actual tenses. Now, for the purposes of our study, we will remain agnostic on this matter, and we will include the future in our study. A second disclaimer I have to put in place has to do with what cognitive linguists call non-canonical viewing arrangements. So for example, when you have sentences like lunch starts at 12 or my mother is leaving tonight, you're using a present tense to refer to a future. And these nuances are very difficult to pick up for a machine, but of course, this flexibility enables speakers to present situations in the way they conceptualize them with relatively few formal options. But what's interesting is that speakers too, language users too, seem to have need for some contextual elaboration when our viewing arrangements aren't canonical. So as you can see in the sentence, lunch starts at 12 or my mother is leaving tonight, the future interpretation is made possible thanks to the temporal phrases at 12 or tonight that are present in the context. And the same can be said to apply to the generic interpretation of the third sentence. Frequently, neither of these strategies will be practical for smaller businesses. Here, it's the adverb frequently that points to the generic interpretation rather than a future interpretation of this particular sentence. So, although we know that our model will struggle with things that aren't implementations of a canonical viewing arrangement, we expect that there will be some contextual element available that isn't the typical contextual element for that tense aspect combination, and that alerts both users as well as our computational model to the fact that something different may be going on here. Now, let me tell you a bit more about the computational learning model we use. So the algorithm we're using is Rescorla and Wagner's 1972 model of classical conditioning. Harald Bayen and Peter Milin implemented this rule computationally in 2011 as NDL, the naive discriminative learner. This model stands out because it's simple, it's powerful, it explains a range of empirical learning phenomena, it's biologically plausible, and it has been said that it has an evolutionary advantage over other more powerful learning mechanisms that are inevitably more costly and more greedy. Now, when I put the formula on the slide here in words, the Rescorla-Wagner rule is an error correction learning mechanism that defines how a system gradually learns to perform a task by associating cues and outcomes. And it learns how to associate cues and outcomes in a way that helps it perform its task, not just from the positive supportive evidence it receives, but also, and in particular, from the prediction errors that it makes. To make the learning experience of our model as natural as is possible in a computational setting, of course, we made sure that it could learn from realistic cues. So we offered it both individual words as well as chunks. So we identified chunks ranging from 1 to 4 words in the contexts that were available in the British National Corpus, and we retained the 10,000 most frequently used ones for each length. So 10,001 grams, 10,002 grams, 10,003 grams, and 10,004 grams. To give you an example of these chunks, so an example of a 1 gram are individual words such as the, or past, or few, or years, or days. When we move to 2 grams or bigrams, we are looking at things like the past, few years, or few days. When we move to trigrams, we will have for the past, or the past few, things like that. And then finally, when we arrive at 4 grams, we have chunks like the past few years or the past few months. Now, as I said, we made it as natural as possible. Of course, it's still a computational model. Computational models can't do everything human beings can do. So in this case, we are looking within the sentence. We are focusing on the experience or the information that is provided through language within a sentence alone. Please don't conclude that I think that's all there is to the expression of time or that's all there is to human experience. Of course there is not, but that's currently what we are able to model computationally. And you'll see that the results really are very interesting, even though the input may seem impoverished compared to what we as humans have access to. So as I said, the model then gradually learns to associate these cues with specific tense aspect combinations, which are our outcomes. Let's have a look at the sentence. Since then, he has managed to remain the spiritual leader of his people, extracted from the British National Corpus. What would be the cues and what would be the outcomes? So the n-grams we just talked about, they are the cues, as is the lexeme managed in green here on the right. We thought it would be unfair on the model to have to predict what the speaker is going to say, rather than only how they're going to say it, which tense aspect combination they're going to select. So these are our cues, and then at the top, the tense aspect labels, those are the outcomes. So the algorithm gets a lot of information, but not the actual verb form has managed. And then the algorithm figures out which cues are good predictors for the outcomes, given the way in which they occur. But it adjusts the strength or the weights of the relation given the errors it makes in the process of learning. So the algorithm then figures out which cues are good predictors for the outcomes given the way in which they co-occur, but it adjusts the strength or the weights of the relation given the errors it makes in the process of learning. We can see, for example, that the cue since then dislikes the present or past simple. The connection line is cool blue, but it loves the present perfect, and the connection line is hot red. And once training on a large sample is complete, we can then go in and see whether the algorithm prefers the same tense aspect combination that the writer of the sentence originally used. In other words, we can then determine whether our model would prefer the form has managed when shown the sentence at the bottom of the slide. Now, the data we trained our model on is taken from the British National Corpus, which is a collection of 100 million words of mainly written and some spoken British English. And the setup that we used for our study is typical for any machine learning study. So 90% of the data was used for training, so we had more than 6 million training events. We then had a test set that consisted of 5% of the data that hadn't been used for training, and another 5% of the data was used as a validation set, also hadn't been included in the training events. So the cues that we used, the n-grams, 1, 2, 3, and 4 grams, as well as the infinitive, the lemma of the verb we were looking at. There were 44,000 of those, and all this information was used to learn to use 11 outcomes. There are 12 tense aspect combinations, but we had to omit the future perfect progressive because there were so very few examples available in the corpus that it wasn't possible to train a model on. I think there were about 30 examples only. Overall, the prediction accuracy of our model is 68%. That means that in 68% of all cases, the algorithm's first choice was the tense aspect combination that was originally used in the sentence as written by the author. And that's an excellent result. On an 11-way choice, simply guessing would give you only 9% correct. And always choosing the most frequent option, in this case the present simple, would get you 46% correct. So 68% is a serious improvement. But of course, is it fair on the model to only take into account the first choice it makes? Because in many instances, multiple options are possible. And if we take into account the top 3 choices that the model makes, then it gets 93% correct. Now let me convince you that this is a fair thing to do. So we presented 60 native speakers of English who were given sentences from the BNC with the verb form removed, which is exactly what we gave our algorithm. In this case, you have pleased to meet you, he, and then the lemma reply. So which of these possible options would you choose? He had replied, he has replied, he replies, he will reply, or he replied. So if we look at what our native speakers chose, then we see that the overwhelming majority, nearly all of them, chose replied. So pleased to meet you, he replied. And some of them think that the present replies is also possible. Now you see, in this case, the 60 native speakers of English are in very strong agreement. And we noticed that when the algorithm or our model was certain of its choice, native speakers also tended to agree. There are, of course, other options. If you look at a sentence here on this slide, if you a form of plan on staying, I suggest you move your stuff to one of the other bedrooms. So the options here are if you have planned, had planned, were planning, are planning, or plan. So what would you personally prefer? If you can't make up your mind, that's not really a problem, because our native speakers of English gave a varied number of responses. In principle, there was every potential tense aspect form that we offered was chosen by at least a few participants, although the majority chose if you are planning on staying or if you plan on staying. Some of them seem to think that if you have planned on staying, if you had planned on staying, or if you were planning on staying are also possible options. And, you know, native speakers clearly here diverge in opinion, so it is also only fair that the algorithm would be less certain of its choice. So that's just to make a case for allowing or taking into account the three best options that the algorithm proposes. So overall prediction accuracy goes up to 93% overall, but what remains very visible or very striking is that the bulk of the correct predictions are still made for the present simple and the past simple. So the present simple is predicted in 86% of all cases, past simple in 73% of all cases, and it remains very low for the other tense aspect combinations, below 5% in total. So you could simply conclude that learning follows by and large the natural frequency distribution that you can see in the pie chart in the upper right corner, and I've matched the colors. So you see that the present simple is in blue, the past simple is in red. They make up the bulk of the usage, and maybe that's just what our model picks up on. It's well known that most things in language have a Zipf-ian distribution, which means that a few things occur very often and most things occur relatively rarely, and things that occur more frequently are learned better. But when we did some digging, we had to come to the conclusion that this is not what we are seeing here. We didn't find any correlation at all between the frequencies of cue outcome co-occurrences and the association strength between the cues and the outcomes. So in other words, it's not because things occur frequently together that they become strongly associated with each other. Frequency of occurrence does something different here. Now let's take a look under the hood and inspect the cues that drive our findings. Now, if you just eyeball this table here, you immediately discover this clear split. The present simple and the past simple on the left-hand side are strongly supported by the lexical items on which they are encoded themselves. So there are verbs that themselves are very strongly associated with present simple, such as thank, suppose, hope, remember, and there are verbs that are strongly associated with the past simple, such as he replied, he whispered, he murmured, she nodded, she smiled, etc. Other tense aspect combinations, such as the present perfect and the future simple on the right hand side, are strongly driven not by lexical items themselves, but by contextual engrams. So for the present perfect, we have things like we already, since then, I already, traditionally, over the last, etc. And for the future, you have things like that point towards the future. It is hoped, hopefully, in a minute, etc. So this will remind you of what corpus linguists found, who have long argued that theoretical linguists should stay much closer to the data than they are currently do. And in a sense, our results confirm what the corpus linguists had found, but by doing this computationally rather than manually, we can work on a much larger scale than corpus linguists can, and we gain further insights about language, but also about learning. The chart that you see on this slide contains the distribution of each cue type, so contextual n-grams versus lexical cues. Each has a different color. The lexical items are in bright pink. And so this is the distribution of each of these cue types in the top 100 cues for each tense aspect combination. And you can see that, relatively speaking, the present simple and the past simple rely on lexical cues in bright pink, while the other tenses are supported by n-grams, contextual elements, and they are indicated in any of the other colors. So, in other words, what frequency seems to be doing here is that the frequency with which tense aspect combinations occur decides what type of cue can come out tops. So, frequency of occurrence and the Zipfian distribution of these tense aspect combinations in the input seems to play a crucial role in the cue outcome dynamics, and we think that is the case because our lexical inventory is finite. So verbs will have to be repeated once the tense aspect combination becomes highly frequent. So there are tense aspect combinations that occur less often than there are verbs in the input, and those are cued by n-grams. But there are also tense aspect combinations that occur overwhelmingly more often than there are verbs in the input, and those are cued by their own lexemes. So when you look at frequently used tense aspect combinations at the top here, such as present simple and past simple, they are instantiated by more than 3,000 different verb types, and those verb types are repeated many times, yielding 162,000 and more instances of the present simple and over 131,000 instances of the past simple. Now, there's also a middle layer of tense aspect combinations that have between 1,000 and 1,500 types that are each repeated 5 to 10 times. And then there is a bottom layer of rare tense aspect combinations where we are down to a few hundred types that each occur only once or twice. And this brings us to something that you were probably not expecting after a computational modeling study, but it does look like our findings reflect 3 dimensions of experience: proximity versus distance, certainty versus uncertainty, and simplicity versus complexity. And these concepts have been discussed extensively in cognitive linguistics. You'll recognize this figure as illustrating Lanneker's elaborated epistemic model. An epistemic distance captures the location of an event relative to a speaker's sphere of knowledge. So for our tense aspect structures, this would mean that the present simple and the past simple would be at the core of this graph. They refer to immediate or known reality, of which the speaker is certain, and this is conceptually simple. It comes as no surprise then that they are very frequent. These temporal arrangements are easier to conceptualize and talk about. And because of the frequency with which these tense aspect combinations are used, lexical cues can come out strong. The number of times we use these tense aspect combinations far exceeds the number of lexical items we have at our disposal, and verbs have to be repeated. So everything conspires for us to learn these simple tense aspect combinations really easily. Other tense aspect combinations either refer to unknown reality, which is uncertain, as is the case of the future, or they refer to conceptually complex temporal arrangements, such as events ending in the past before another past event commences. And these are cognitively demanding situations to conceptualize and express. Look at these 2 sentences, one taken from the B and C, the other one adapted. They express more or less the first thing. So the officers tried to stem the flow of blood, the paramedics arrived and took over. This sentence expresses a particular sequence of events with simple past verb forms. But the second sentence squeezes in past perfective progressives, which requires reversing the order of events. So here you're saying paramedics were at the scene in 4 minutes of the emergency call and took over from officers who had been trying to stem the flow of blood. So you see that the way in which you sequence your events is reversed. It's straightforward in the sentence that uses the simple forms. It's very complex in the sentence that uses the more advanced tense aspect combinations. And it's no surprise, this is conceptually a much more complex operation to accomplish. Narrative sequencing is considered an advanced writing skill, and it requires explicit teaching, which is supported by reading the right kinds of texts. This situation creates a bit of a vicious circle. So complex tense aspect combinations are used less frequently because they are cognitively more demanding, but because they are used less frequently, they're also harder to learn. It takes much longer to build up evidence of rare things, and this may be another reason why cues are contextual. So there are plenty of verbs to go around, so n-grams are the more stable element. And this creates a bit of a vicious circle. So complex tense aspect combinations are used less frequently because they're cognitively demanding, but because they are used less frequently, they're also harder to learn. It takes much longer to build up evidence of rare things. And the fact that they are less frequently used may also be the reason why the cues are contextual, as I explained. There are plenty of verbs to go around, so the contextual elements, the n-grams, become the more stable element. So the important lesson to take away here is that because of the frequency with which the simple present and the simple past are used, lexical cues can come out strong. The number of times we use these tense aspect combination far exceeds the number of lexical items we have at our disposal, so lexical items have to be repeated. So in a sense, everything conspires for us to learn these simple tense aspect combinations really easily. They're frequently used, and they have clear and simple lexical cues. Other tense aspect combinations are rare, which means that there are plenty of verbs to go around, so the verbs are not repeated and do not come out as strong cues. Instead, contextual n-grams are the more stable elements, but these n-grams are 1, 2, 3, or 4 word sequences. They are compound cues, and compound cues, things that consist of many parts, are harder to track and learn. So in a sense, everything conspires against learning these complex tense aspect combinations. They are rarely used, and they have fuzzy and complex indicators. So in other words, to someone who learns the system from use, the system looks very different than a linguistic system of tense and aspect would lead you to believe. It seems that there are two systems, but they're not tense and aspect. They're a simple lexical system and a complex contextual system. And these are shaped by cognition and usage in such a way that one is eminently learnable and the other one less so. So what transpires here is that in order to draw an accurate picture of what is at stake in a linguistic phenomenon, it pays off to take a look at actual usage, ideally usage in context, as corpus linguists have been advocating for decades, but taking a computational approach and using the algorithm we can do this on a large scale, and we can do this in a holistic and cognitively realistic fashion that's anchored in principles of how we learn from input. So, in addition to staying faithful to the raw input and to the cognitive commitment, the simplicity of the algorithm offers the added benefit that the workings remain transparent and easily tractable, which cannot be said of the much more advanced deep learning networks that are currently available. Using a simple algorithm makes it possible to understand how exactly certain connections come about. And this in particular will be well received by linguists who will appreciate the fact that the output of a computational model of the type we are using remains accessible for post hoc semantic analysis. So, time to wrap up. I hope that this case study has convinced you, or has shown you at least, what an interdisciplinary approach to language in use has to offer in terms of linguistic description. But what does it have to offer the disciplines involved? So as I said at the start, linguists are in a sense interested in the end result of learning, and psychologists are interested in the process of learning. We think we can fruitfully combine these myopias of psychology and linguistics because the process can help us understand the end result. So if we let learning constrain the linguistic units and generalizations that theory allows, we will have found a natural way to operationalize emergence and stay faithful to human cognition. But the end result also helps us reverse engineer the learning process. So language is the most complex system humans learn to use, and its complexity challenges learning theory immensely. Working with a Q inventory of the size that is required for language will definitely yield new insights into the mechanics of learning. It may be that our neat linguistic tool cabinet should look more, or we should let the neat linguistic tool cabinet look more like a messy tool drawer, meaning that grammar may be more concrete than we think if we stay faithful to our lived experience and the linguistic input that we receive. And as Sinclair put it, grammar is nothing but a generalization over the usage patterns of individual words in utterances. And we think that by taking this computational approach, we have a way to chart these patterns on a large scale while remaining faithful to the input that language users receive. And on this note, I will wrap up. So in a sense, this case study presents a case against too rigid an interpretation of structure or grammar. So the patterns that language users detect in the data may not look the way we linguists expect them to look. But that's what happens when we let learning play a role in shaping the system. And if we learn from data that is as raw as possible and not enriched by any abstract linguistic notions. And I think this is something we usage-based linguists might want to consider doing more of if we want to demystify how structure emerges from exposure to usage. I think such an approach provides very valuable insights into the kinds of generalizations or abstractions that can lay claim to cognitive plausibility and that should have a place in our theory and in our way of describing and accounting for language. And I think doing more of this work, computational, involving learning on a large scale, may ultimately change the way in which we think about language. Thank you so much.